my name is Wouter DeVries, work at TNO, and I will talk about heat integration in carbon capture plant. So this work is part of High Record. I think like most presentations here. And actually within the High Record project, we have a KPI to achieve 60% final energy reduction. So that means that we reduce the energy input of the carbon capture process by 60%. And the main energy input we can see is the in solvent regeneration. So in the stripping steam that was mentioned before. And the way we can achieve this is by applying a heat pump. So then instead of using conventional methods to produce the low pressure steam that feeds the reboiler, we now use a heat pump instead to produce this low pressure steam. But yeah, a heat pump is so efficient because it has the waste heat recovery in the bottom. So this is sort of a general schematic of what a heat pump looks like. We have electricity going in, and we have a waste heat source, and then via the first law of thermodynamics, we end up with a certain amount of process heat. And then the reason we have electricity input is because we use a compressor to elevate the temperature of the low temperature waste heat sources up to the required required temperature level of the process. So my main work was in finding suitable waste heat sources inside the capture process itself. So we can sort of determine a quality of a waste heat source. It's mainly temperature, but also the phase of the waste heat source. It can be gaseous, liquids, or can be a phase change happening. And to achieve this 60% energy, the 60% energy reduction, we actually need to have a coefficient of performance, which is the ratio between the amount of heat or useful heat we provide and the amount of electricity we put in of 2.5 or higher, if possible. So this was the reason I let Babis present first, because this is sort of the product of his work. So here in the bottom right, you can see the amount of thermal energy or duty we need to put into the capture process. So the bottom right is the reboiler. It's about 5 megawatts, and this is for the process of Cao Hellas, which it's about 5.5 tons per hour of captured CO2. And here we assume actually that the reboiler duty is at 120 degrees, and to allow for for an approach temperature inside the heat exchanger, we assume that we use 125 degree steam to provide this heat at 120 degrees. And then the main, let's say waste heat sources, which are cooling demands from the perspective of the capture process itself. Then we have the lean solvent cooler, which has a duty of about 2 megawatts, which is right upstream of the absorber. And then the other one is the condenser, shown here in the top, about 1.8 megawatts of thermal capacity. And I've also noted the temperature levels here. So the lean solvent cooler is roughly 80 to 40 degrees, and it's all sensible heat. And then the overhead condenser is about 140, let's say, 140 to 40 degrees, and there's some water vapor condensing in there. Then I also use some data from the compression train. So for most applications, we will need to compress the CO2 up to say 150 bars, and this sort of shows the conventional or a possible process to achieve this. So we have 4 compressors in series, and each one has its own, let's say, intercooler. And the reason we do this is because we need to cool down the CO2 before the next compression step to avoid damaging this compressor. Otherwise, we would reach hundreds of degrees CO2 temperature. And also here, this duty is about a megawatt, and the temperature range is similar to the condenser I mentioned before. Then onto some heat pump theory. I hope it still works right before lunch, but you can sort of, the ideal heat pump, you can determine this efficiency only using the temperature levels. So if you have a sink in the source temperature, you fill in this equation in Kelvin, I should say, then you get what the ideal COP would be. So if you have a very fully reversible process, then this would be your efficiency. But yeah, we live in an engineering world, so we take 50% of this, which is sort of the, yeah, let's say, commercially achievable efficiency that you can buy off the shelf for a high temperature heat pump. So then we can find what kind of, so for a given sink duty, so this is this 5 megawatt I mentioned before for the reboiler, then we also know that we know the temperature levels, then we can find the actual COP, and then we can find the amount of shaft power, of compressor duty or compressor work that needs to be put into the process. And then again, we can find the amount of source heat that we need. And finally, we can sort of determine at what temperature level should we extract this heat from the capture process to be able to actually achieve this Q source I mentioned here. So to summarize, so the amount of heat that you need is actually determined by the efficiency of your heat pump. So if your heat pump is less efficient, then you need to put in more shaft power for your compressor, and therefore you would need less waste heat. And it also works the other way around. But I think I have some numerical examples later on. So what could such a heat pump look like? So as summarized before, we have a heat pump sink shown here in the top at 130 degrees. And then because again, we have this 5-degree temperature difference to allow heat transfer from the working medium inside the heat pump to the low pressure steam, which then transfers the heat to the solvent inside the reboiler. And on the source side, I've actually shown two heat exchangers here. We also assume an approach temperature, but we chose slightly higher, about 10 to 15 degrees, to have some freedom in actually designing the heat exchangers. In the end, I analyzed 6 different concepts. This is one of the concepts shown. I sort of call this the 2 compressors in parallel process. And actually, you have one compressor here, one here, and they both operate at different temperature levels. So you sort of split the waste heat temperature into 2 levels. And also because we use try to use actual compressors, which have oil as both a lubricant and also a sealant, which also needs to be cooled. We also can add this as an available waste heat source to our pool of sources. So here I list all the concepts that are analyzed. It goes from, let's say, the basic integration concept. I just showed you the second one, but we also have the one where we add the compression train intercoolers. So the concepts A to C do not consider the compression train. So for applications that don't need this, you can use these concepts. And then we also, I've also added 2 concepts which are just 2 previous concepts combined together. And then, without going into all the detailed calculations behind it, this is sort of what you get as a result. So again, concept A to F. And then the red line shows the threshold of 2.5 I mentioned before that you actually need to achieve to reach this 60% reduction in energy. And what you can see is that all concepts except for let's say the basic integration concept are able to achieve this COP of 2.5. But in the end, I selected the most promising concepts. So concepts E and F, which are the combined concepts for detailed analysis. So maybe I should stress here that all this analysis has been done based on this equation I showed before, where we assume that our heat pump has an efficiency which is equal to 50% of the Carnot COP. So no working medium and that kind of stuff yet. But that's the next step. So as mentioned, concepts E and F, and then based on the temperature levels, I select isopentane as a working medium, which is, let's say, commercially available. And here I actually found that one of the concepts, so concept F, where we have two compressors in series, is practically unfeasible. And the reason for this is that the Carnot COP actually, it sort of breaks down at very small temperature differences. So because we have two compressors sort of stacked on top of each other, then the temperature lift is too small to be commercially feasible. So for this reason, I've chosen concept E as the final concept. So then we have two compressors in parallel, and then we also have added the compression train intercoolers as a waste heat source. So then onto the results. So in the end, I managed to reach a coefficient of performance of 2.757. And this is distributed over two compressors which operate in parallel. But then, so there's the primary compressor which operates at quite a high evaporation temperature. And then the secondary compressor operates at a much lower evaporation temperature. So what I actually do is I split each of the available waste heat sources into several temperature levels. So as you can imagine, for example, the lean solvent cooler, it's a temperature glide from say 70 to 40 degrees, and then I choose to extract some of the heat for, in this case, only at 50 degrees, and then the rest of the heat is just dumped to the conventional cooling, the conventional means of cooling, so probably a water circuit or something. And you can do something similar for the condenser, heat pump, oil cooler, and also the compression train intercoolers. And then if you do this exercise, you end up with a final or total electricity input of about 2 megawatts. And here I also allow 5% for things like oil pumps, heat tracing, heaters, all that kind of stuff. So this is my last slide, which sort of shows let's say the product of the work within the High Racket project. This shows the integrated heat pump and CO2 capture plant. So here in bottom left, in the dashed black lines, we have the capture plant or the solvent loop, and then the purple section in the middle shows the steam system, which is rather small, I'd say. And then we have the primary loop in orange, and then the secondary heat pump loop in red. And then, for example, here we have then the lean solvent cooler. So about 1 megawatt of the total of 1.7 is used for the heat integration, and then the rest is deemed to be of too low temperature to be used, and then this is used or rejected using conventional cooling means. I think maybe one of the most important results is that Bob has calculated for the conventional process without any heat integration that you would need about 3.3 gigajoules per ton of CO2 captured. And then by doing this exercise, you can bring this down to 1.3 gigajoules per ton of CO2 captured. And with all the so if you consider electricity, so let's say the stuff you actually pay for, then you end up with 60.3% of energy reduction. So in the end, we reached this 60% of this KPI of 60%. That was it from my side. Are there any